Right. Hi, I'm Kev. Thank you for coming along. I'll get started. I imagine as other tracks finish, more people will arrive, and I'm just going to blaze on as if they're not there. So, thank you for being on time. You're the best. You're the heroes. So I'm going to talk about detection and blocking with BPF via YAML. And I'll explain roughly what those things are as we go. The obligatory, who am I slide. I've worked for a number of interesting places. Most recently, though, was, I've got Microsoft there. Yeah, out of the way. Microsoft sysinternals, where I ported Sys1 from Windows to Linux, which you may or may not have seen. It's open source, Sys1 for Linux. It's on the sysinternals GitHub. Sys1, if you don't know, it has a user space component and then a Windows driver, which collects all the information about what's going on in the system, sends it to the user space component where it gets filtered and then output. And the user space part controls the configuration. So on Linux, it is a case of porting that user space code, which is allegedly POSIX compliant already, and replacing the Windows driver with something that could collect events on Linux. And in this case, we use BPF because the only alternative is a kernel module. And if you make a kernel module, you have to compile it against whichever kernel you want to run it against. So if you're trying to release a tool, you end up having to compile your kernel module against every kernel, which obviously is impossible, or give the users the challenge of compiling it against their own kernel, which not everyone wants to do. Lots of good reasons. Shortly after releasing that, I moved to Isovalent. Isovalent you might not have heard of. We employ a lot of the people who build BPF in the kernel. So we've got a load of kernel hackers. When you look at a Linux Plumbers Conference photograph for the BPF track, you sort of confuse it for an Isovalent team photo because there's so many of our people there, which is kind of cool. And I work there doing similar things. And I'm basically going to talk about some of those things. The other thing I do, which I always like to stick into a presentation, is I run a blog with my wife called Cosmic Pancakes, which is all about the weird and wonderful world of hypnosis. I've just finished a master's degree in psychological methods to start a PhD in September. It's fun. We mostly laugh at old hypnosis books for being rubbish, and we interview some really cool people. But it's just there, just as that's my side project. So I'm going to talk about logging. I'm going to make logging interesting. Obviously, I didn't put it in the title of the talk because then literally no one turns up. But, logging is really important. Like, it doesn't matter whether you're, a red team or a blue team or a purple team or whatever. Like, you need logs. Logs are the only thing that's going to make anything more secure, is like actually knowing what happened. If you don't know what happened, you've got no idea what worked, what doesn't work, what went on, who did it, etc. So logs, most people collect logs. And my hand-wavy argument today is that you're doing it wrong and you should be doing it differently. I'll talk about BPF for those who didn't see my talk a year ago at, say, Forcon or some of the other places. I'll talk about what BPF is and how it works. I'll talk about the tool, open source Tetragon, that we've released that will help with this. What it includes, show some examples, hopefully with some live demos. Not that they're massively exciting, but everyone wants to see the tool actually work, don't they? And where we're going. So, logging. If you look at a logging system, it always reminds me of this. This is like the stickers on the bottom of the pieces of hardware you buy that tells you that you can't open them and there's nothing inside to service and you can't take it apart and you can't modify it. Because most logging systems are kind of like that. Yes, you can configure them, but within the bounds of what they let you configure. Now, if you imagine that there's, 350 people in the conference and you all have, a good understanding of security, I don't think any of us could predict a new technique that's going to emerge next week, next year, whenever, that use a completely new way of maybe getting code to run on somebody else's system. Now, if we can't predict that, what chance has your logging vendor got to be able to predict that? Whether it's K-Audit, which is the kernel component of Audit D, whether it's an EDR, whether it's an expensive solution, a freeware solution, of whatever. If they can't predict the technique that's going to emerge in the future, then how do we know that they can log the information that you're going to need? And what do you do in the meantime? Like, you're going to wait until they bring out an update that then can detect the thing that you care about? So my argument is, don't buy or install a logging system, but build your own logging system. Like, if change is the only constant, then you want to be able to change your logging system. And that doesn't just mean configuring it within the bounds of what they let you do. It means changing your logging system to be able to detect the things that you now know you need to detect. That's the hand-wavy bit. But ultimately, that's what this is all about. So I've been speaking about BPF for a number of years at various places, and you can find some of those online if you really want to look. But this talk is going to be slightly different. So if you haven't seen my talk from 44Con, and you want to, maybe, there's a URL where you can go and find it. But I will talk a bit about BPF. It is powerful, it's mostly do-it-yourself, and it is really difficult because of that. So it's regarded as the biggest change to the Nix kernel in 50 years. So, if you've used T-Shark, TCP dump, Wireshark, and you've filtered what packets you want, like you put it there, not port 22 or whatever, you've actually used classic BPF, which stands for Berkeley Packet Filter. Your filter construction has been turned into BPF machine code, which is its own virtual CPU essentially, a RISC-based architecture. And then that's being inserted into the kernel at the point where it can spot packets. And then it runs that code, which is jittered to your native machine code, on every packet it sees. And if it matches, it then sends that packet to user space. And if it doesn't match, it doesn't. And the reason for that is because there are so many packets going through the kernel, you can't send them all to user space and then let user space filter them out. And you can't build a logic, like a configuration logic, to tell the kernel what kind of packets you want, because you can't predict what packets you kind of want in the future. So instead of like constraining it to some sort of logic based on what they thought you might need, they instead built a virtual machine in the sense of a virtual CPU rather than a VM. So you run code in the kernel to make those decisions, which makes it eminently flexible in what kind of packets you send to user space to then print out or whatever. What happened then was someone said, if we can run code in the kernel on every packet that arrives or leaves, why can't we run code in the kernel on any events? And it's like, yes, why not? And so eBPF was born, extended BPF, although it's no longer an acronym, it's now just a word, eBPF, for reasons, possibly because it's got very little to do with the Berkeley packet filter anymore. So you can write code in C, you can insert it into the kernel, you can hook it on any kernel function, any syscall, any trace point, any network hop, and when that thing happens in the kernel, your code will run, which is kind of cool. You can do that with kernel modules already, but with this, you can do it in a portable fashion. You write your code once, compile it to an ELF, you can ship that ELF to any Linux system pretty much that supports BPF, and it will run. So, it is amazing. Like, with very little work, you can get code running in the kernel on every time a particular thing happens. And from there, you can gather state, you can see things, you can store it, you can send it to user space, you can store it in a fashion that other BPF programs can see it, you can store it in a fashion that user space can see it, user space can update that memory. It's kind of cool. But it is a programming language, right? I mean, BPF is literally an API. There's a syscall called BPF, which makes it really hard to do. There are like tools out there, like Sys1 for Linux, and Fock1 for Linux that run on BPF, but they're not a lot different to Kaudit or any other kernel module kind of based solution. Like, they're using BPF to achieve their aim. They're not giving you the power of BPF to do whatever you want with it. If you want that power, you kind of have to write it yourself, which is what my talk last year was all about, and mostly about how difficult that is. Which, if you're interested, go and have a look. It will blow your mind as to how how difficult it is. The biggest thing in there is the verifier. So in order to make it safe to run code in the kernel, because obviously you could crash the kernel if you could run any code, your program goes through a static analysis on load through a process called the verifier, which runs in the kernel. And that checks that your program is going to finish within 1 million instructions. It's going to check that it doesn't do any illegal memory access. It's going to check that it doesn't, deref any null pointers. That you only use the helper functions that you're allowed. Yes, you can't run any arbitrary function in the kernel. You can only run the helpers that BPF give you, which proxy essentially functions from the kernel. But different programs attached to different places get different sets of helpers depending on what they do. So the verifier has to check that you're using the right ones and you're not using any others. The other thing with the verifier where it becomes a nightmare is you have to optimize your code. If you compile it with something like Clang, you have to optimize it in order to get it loaded into the kernel in the first place because it needs to be optimal. But in doing so, Clang will optimize out a lot of the checks that you put in place to satisfy the verifier. So for example, if you've got like an index into an array and you don't constrain that in any fashion, then theoretically that index could take any number that variable could hold. Like if it's a 64-bit number, literally any number in the world, obviously to a degree. And the verifier will spot that and say, well, your index could be bigger than the array. So you put a check in that says, if I is greater, is less than such and such, do the lookup. And Clang kind of like, when it's optimizing your code, realizes that you don't need that check because it can't possibly be bigger than this number because you've got to check somewhere else. Optimizes out your test. And then the verifier says the same thing it said a minute ago, that this variable could be massive. You're like, how could it be massive? Because I've got this check. But then you go and look at the BPF machine code that it's generated, and you realize your test is missing because Clang's optimized it out. So then you have to go back and write some inline assembler at that point in order to put the test back in such a way that Clang can't optimize it out. So it does become, and that's the simple case of where Clang messes with your life and causes the verifier problems. It gets worse, but as I say, see the other talk if you want to know all the details. So my argument is why don't we make a generic tool that gives you all the power of BPF without any of the coding? Most of what you do with BPF, the code is pretty much the same. So why don't we give you that option? Why don't we just put that together? And that is where Tetragon comes in, which is open source. And if you go to GitHub, Cilium, Tetragon, you can get it. There's all sorts of images available which you can download and run. There's documentation on how to use it, how to get it, etc. So what you're basically doing is you feed YAML into Tetragon. It attaches to the kernel hooks that you've specified. It analyzes the data that's there every time those hooks get run, and it sends the data back to user space in order to be sent out as a log, however you want to output it. I'm sure everyone knows how to write YAML, yet another markup language. I mean, my son is 14 and he can write YAML, mainly because Minecraft mods are configured with YAML, and therefore he's suddenly got really good at that. But if you're not used to it, there'll be some YAML later on so you can see. So we've hidden all the code. Obviously, it's open source. So if you do want to contribute, there's a lot more work to be done here. Please do. But you don't have to. You can just write YAML and this will all just work. It knows about complex data types. So where you're hooking in the kernel, you'll have pointers to all sorts of things at the kernel function that you've hooked. And what you don't want to see in user space is just a memory location as an argument to a function, because that's pointless, literally pointless. But so instead, Tetragon knows about things, and it will actually extract the information from those and put those into the messages. So you get a richer kind of thing. And we can copy stuff on return. So sometimes the hook itself, the parameters aren't that much use on the entry point to a hook. So if you've got like a read function that's reading from a file or reading from the network or whatever, then the buffer as a parameter to that function is going to be empty or possibly empty on the way in. It's certainly going to be of no use to you. It's not what you want to see. You want to see it on the way out. Well, we can copy buffers on the way out as well. So we can capture that, quite easily. At the point where you hook, you can match on all sorts of stuff. So there's logic you can add to it where you can check which PID binary obviously it's container aware. We also make Cilium, which is a CNI for Kubernetes. So we do a lot of Kubernetes type stuff. So obviously Tetragon is very Kubernetes aware, but otherwise it's container aware anyway if you're not using Kubernetes. I'll talk about following file descriptors and tracking sockets later. It'll output to gRPC, but obviously logs. It's the sort of things you expect. We can also trigger canaries. The guy this morning mentioned canaries. I assume everyone knows about canaries, but if not, we'll see some canaries later. It's all in YAML. You tell it what you want, where to hook, what you want to do with it, what you want to report, and it will do those things for you. Where you might want to use it is replacing your logging system. So you can build a better logging system that you can change, a logging system that you can control, a logging system that will detect whatever you tell it to detect. Not what your logging system provider thinks that you should be able to detect. And but we can also do some cool stuff, like we can block functions from running, and if we choose, we can kill a process as well. I mean, there's a choice between when do you block and when do you kill. Well, if you're detecting malicious activity, you probably just want to kill the process. You probably want to block the activity itself, but you probably want to kill the process, because if it's already running malicious code, why let it continue? Just kill it. But if you were building something that was constraining what processes could do, so within a certain container, for example, you might only want them to have access to certain syscalls or certain syscalls with certain parameters and minimize what they can actually do. Well, in that situation, you could just block the functionality, but let the program continue, and all it'll get is an error message to say that it couldn't do that particular thing. I'll hopefully demonstrate some of that later. If you use strace, which tracks syscalls, then we can build a better one. We can build one that is really specific to what you care about, that only reports on the syscalls that you care about, but it goes beyond the syscalls and report, information from deep inside the kernel. And an example of that is, so at my company, my manager, is one of the kernel hackers. He's got code in there. He's often debugging his changes to the kernel. And in the past, you could either attach GDB to a virtual machine that's running your kernel that you're trying to debug, or you could stick a load of print K messages in there, which are like printf debugging. And there wasn't really a lot of other things you can do to debug a kernel. Now, we just use Tetragon. We just hook it to the places where we expect to see the thing that we want to debug, and we see what data's coming out of it. So it's kind of cool for that as well. What do you get? You get process management. Obviously, every process that starts or finishes, it will report, but it'll also cache it, and it'll also cache all the useful information about it. And then whenever you have another event, it will match it to the cache and add all that information into the event. So when the event comes out the other end, you don't have to match it in your seam yourself. It'll already have things like, what binary it was, what pod it was in, et cetera, which is kind of cool and kind of useful. So it's a JSON output. That's a process execution event. As you can see, I ran ls-l. It basically tells you about the process on the left-hand side. On the right-hand side is the parent process. Every process has its own exec ID. So you can match that up in your seam. You can build a tree of processes if you wanted. So if you found something that's malicious, you could track back, just find out where it ran from and what its history was. Obviously, an exit one looks just the same, except it's a process exit event, and it has an exit code, in this case status 2. We also provide documentation, etc., and we're hoping to build community around this. We're continuously developing the open source version. We also make an enterprise version for paying customers, which comes with support and extra bits and pieces, obviously, but the open source one is the basis of our enterprise one. We are active developers of that. But as I say, anyone can join the team. It's open source. I need at some point to talk about hooks, right? Because I mentioned them all the way through, and there was no good place in the talk to talk about it. So I thought here's probably as good as any. If you want to hook something, you normally start with a syscall. Would be the easiest thing. This is, for those who don't know, a syscall is where your user space program needs some resource that the kernel has control of, and that's normally files, network, starting a process, forking, things like that. And so you in your program, you call a library function from libc. Libc causes a syscall to happen, that causes a task switch to the kernel takes over, gets access to that resource that you've asked for, does whatever it needs to do, passes it back through the syscall interface, back through libc, back to your program, and then it happens. So if you're opening a file and it gives you back a file descriptor when that file has been opened, the kernel's kind of done that on your behalf through a syscall. So if you wanted to debug, or you wanted to track, or you wanted to log, that sort of thing, you might start with the syscall. And the syscall in this case would be open app. And you can find it normally by looking for, say, sys_open app would be a good way to locate this location. And then you can follow the function. So this website is elixir.bootlin.com. It's got all the source code for the vanilla kernels for every version of Linux kernel, which is really cool. And you can cross-reference between the versions to see what changed, etc., etc. So you can find a hook that doesn't change across versions, for example. But it's also all hyperlinked. So when you click on a function like do sys open, for example, it will then take you to the function do sys open, or it will take you to a place everywhere that calls do sys open. So it's a pretty cool website, and it's pretty awesome. So for reasons that I'll come to later, you might not want to audit the syscall itself, which is kind of what Kaudit does and what a lot of the off-the-shelf logging systems do. Mainly because it's got user space buffers. And the problem with user space buffers, if you saw the Phantom attacks talk at DEF CON 29, is that those buffers can change between when your logging system sees what's in the buffer and when the kernel actually acts upon the buffer. So what you log might not be what the kernel acts upon, which is really annoying from a logging point of view because you've got no integrity in what you're seeing. The Phantom attacks, they managed to use interrupts and timing to make that really, really reliable. So it could literally open etc. password, but the login system would say /temp/foobar. So you might not want to log the syscall itself, but using Elixir, you could click on do sys open, you could follow the functions that get called by the syscall, and eventually you'll find a point where the kernel copies those buffers into its kernel memory. You could then hook a function that comes after that point, knowing that the buffers are now in kernel memory, and therefore they're static, they're stable. It is exactly what the kernel is going to operate upon. So that's basically what I was saying. Follow the breadcrumbs. Of course, the other thing is have the source code locally and use grep judiciously, because that's usually the way that I find things is to grep with abandon. So I'll give you some examples, some trivial examples I might add. Some of these are toy examples. And you might care if somebody changes the time on your box. I mean, if you care about logs, you probably care about the clock being correct, because obviously otherwise all hell breaks loose. So there's a syscall which sets the time, and if you inputted this bit of YAML, it would log every time that syscall gets called and tell you which clock was changed. So, because you don't really care what the time's changed to, I mean, you might care, but you probably don't need to care. What's more important is that someone's changed the clock. And so just to explain the YAML, it's in the kprobe section, which is a probe into the kernel. We're going to use the syscall sysclock set time. We tell it that it is a syscall. That means to look up in the table of syscalls as opposed to just look up in all of the possible functions in the kernel, which is the alternative here. We specify which arguments we care about. So index 0 would be clock ID t, which clock, the first argument. We tell it that it's an int, because the clock ID t is actually an int under the hood. And then we tell it how to match. Like, what do we care about? Well, we care that it's not PID 0 or 1. And we also care in a namespace environment that it's not 0 or 1. So I don't know how familiar you all are with namespacing, but if you have containers, every container has its own namespace, usually its own process namespace. There's process namespaces, network namespaces, mount namespaces, etc., etc. Usually your container will have its own namespace for each of those components. And so in a container, your initial process will be PID 0. But outside the container, that'll be PID, 17,058 or whatever, right? So there's different views from where you sit as to what IDs things have. And if you're using Kaudit, Audit D, or any Audit D based solution, Audit Beat, there's a whole load of EDRs built on it, I don't know if Azure Security Center still is built on that. It was when I was there. Then it's not container aware. All you're going to get is the process IDs and the UIDs and yada, yada, yada from the bare metal from outside of all the containers. And therefore, what is PID 17,058? Well, it's actually more useful to know that it's PID 0 within the namespace in which something occurred, because then it's the first process that ran in a container. So we're excluding, say, PID 0 and 1, even if they're in containers. And then there's nothing else to the YAML. That is it. By default, it will post the action. And so if that gets hit, you'll end up with an event in your JSON, which will go through the gRPC. So you can plug that into anything that can take gRPC, which is, quite a lot of stuff. You can build your own backends onto that. We can push that into, Splunk or whatever. There's all sorts of things you could do. Or you can just have it come out as logs, which is what I'm going to demonstrate today. Another thing you might want to log is the BPF syscall itself. I mean, what if someone's deleting your maps, changing your programs, loading their own programs? For example, there's rootkits written in BPF. You might want to detect that people are loading BPF programs after you've loaded all of yours, of course. Well, you could audit this BPF syscall itself, but there's only one syscall that does a wealth of things. So what's more interesting is to follow those breadcrumbs, like I was showing you on that slide a few minutes ago, and see what it calls. And the sort of things that the BPF syscall calls are these functions: BPF check, perf event alloc, and map alloc. And these are things that occur on, when a BPF program is loaded, when it's attached to a kernel function, a hook, and when a map's created. And obviously there'll be more, right? But it's just an example. And so with this small amount of YAML, you can now detect when anyone is accessing those things. And you can see argument 1, in this case, is a BPF atta. Well, TextCon knows what that is. So it'll unpack that struct and give you the details from within the struct. So you're not just getting a memory location, you're getting the actual information. The same with a perf event or a BPF map. So it's kind of trivial amounts of YAML to do some quite interesting logging. It might be more than just a one-line, please log this thing, which you might get with your normal EDR or logging system, but it's not that much harder, and you get to do anything you want and hook wherever you want. Notice syscall is false in all of these cases. That's because these are just random kernel functions. So any function in the kernel, pretty much, you can hook. Now, we talked before about detection and blocking and killing. There's also alerting. So if you haven't come across canaries are things that you can just litter on your system. So you can put canaries in files which no one should be accessing. If an attacker gets on your machine and opens that file, it fires off a canary. You can have binaries that have got canaries in them. So if someone runs a particular binary, it triggers a canary. And when a canary gets triggered, it basically goes through to a web portal, run either by Think's Canaries or Canary Tools, which is their open free version of canaries. And then it will do what you want it to do. So, like send you an email, send you a Slack message, text your phone, whatever. So we can support all 4 of these sort of things. So if you just had the YAML in black, so this is a bit of a toy example, and I'll come to why in a minute, but maybe we care about someone creating a symlink to accept a password, right? Now, obviously, the symlink at syscall, this is one of the examples of why you might not want to, log on a syscall itself, is because the buffer could change for a start, but also it's a text buffer. So, if you link to /etc/password, that's fine. That's a string that you might want to match on that. But there's also like directory traversal. You could already be in the etc directory and just symlink from password to something else. So just to solve that, I've just said match on anything that ends in password, because that will catch all of those. Obviously, it will catch a lot of other things, which is why it's a bad example. But I'll come to the solution for that later. But if you just had the YAML in black, what it would show you is it will highlight all 3 of the arguments. So from what directory ID and where it's going to be linked to, and it would just spit out JSON when it happens. So what time is it? Past. You've probably got time. So let's have a quick look at that So, the trusty online demo, which I can't see on a screen here, which is kind of annoying, but never mind. I should have some YAML, and that's the YAML from the slide. And if I launch Tetragon with that YAML, right, so that will spin up Tetragon. It's got a lot of stuff to do. It's going to hook. Now it's listening. Right, so then we could tell the events that are coming out of it, which reports all the processes that get run. I mean, that was the process we just ran, was the tail, or the grep rather, probably. And then we could make a link from etc password to P. And in here, we'll have an event, as you would expect. So if I just pop up a little bit, that's the exit. There's the event itself. So it's a Kprobe event, as you can see. It's telling us that it's ln, it tells us the command line, it's got its own exec ID, it's got its parent, as you'd expect, and as you scroll down, you can see that was the syscall that got called, symlink at, and it's got the parameters that it gave. Right, so that's kind of detection working. If we added the bit in green, not only would we get the event, but we'll also get an alert. We'll alert on it by doing a DNS lookup to a particular domain, which is going to be our canary. So I'll quickly show you that. Say quickly, as quick as man's possible to show. So we'll just swap this out for the alert YAML. I don't think it's me. Right, so if we were to create that link again, and we go and have a look in our log, you can see there's the tail end of that Kprobe again, but this time it's got the action DNS lookup, because that's what it's gone and done. I don't know if you heard the noise on my laptop just then over the mic, but that was a Slack message that I just received to tell me that someone's tried to link from a sector password, which is kind of nice. If I was to look in, check my email, I've got an email from Canary Tokens to tell me that someone's been looking. When I did the demo, it can also text you, and there's all sorts of things you can get canaries to do. It's quite nice. So from all the way, I mean, it's a lot of machine. That's not logged in, but if we were to log into there, we'd probably see the canary has been detected. That's in our console. So it's a lot of machinery. Oh, that's the wrong one. It's a lot of machinery in order to get something happening in your kernel is now sending a message to your Slack. But it's kind of cool that you can do that. You can literally trap anywhere in your kernel, and it will tell you in your Slack message that someone has done that, or you've just done that, which is kind of neat. Blocking and killing. So if we had the text in black, which is the same, and then we added the blue bit, that would block. And so what it's going to do is tell it, you can't have this syscall, and I'll give you an error code of -1. So I can demonstrate that, and then if we had the bit in red added on as well, not only will it block it, but it'll also kill the process. So I'll quickly show you that, because why not? Cut back to here, kill that, run it back up. We do it with block. So that will load up. It's listening. Yet again, then we do the link. This time we get an operation not permitted. That's because the syscall failed, and then the tool is then reporting back to us that it failed. So that didn't run, and the link wasn't created, so it's literally blocked. But equally, if we were to do the same thing, but this time tell it to kill, load. And then we try to make the link. This time we get told killed, and the process itself, and also, as before, obviously it didn't happen because it got blocked. So you have the choice, as I said before, whether you're constraining what a process can do because it's within a container where you don't want to give it access to other stuff in a set comp kind of way, but better than set comp because it's not just you can have these syscalls and you can't have those syscalls. It's you can have these syscalls with these parameters based on what we care about, whether the values are bigger or smaller than certain numbers, that they begin or end with certain strings, etc., etc. But if you're detecting malware and you think that whatever's happened is horrible, then you block it and you kill it. So that's basically what I wanted to show there. So I talked about files, particularly the symlink example, being bad with files. Why are files so difficult? Well, when you open a file, or you create a file, for example, you might use the open syscall, the open at syscall, or the create syscall. All of those could create a file, and they'll give you back a file descriptor. But the path you provide it could be, it's whatever the user gives you. And in the kernel, where we detect this, all we're going to see is that buffer. Well, of course, we might not see the actual buffer because of the phantom attacks. We might be seeing the wrong buffer. But if we assume the buffer is okay, it could have, it could be relative, it could have directed traversal, etc. And they're really difficult things to try and resolve in the kernel. You've only got a limited amount of complexity, and you also don't want to be taking up too many cycles in the kernel, because obviously that's going to slow down your whole system. If every time one of these syscalls gets called, you're trying to unpack or resolve a particular file name. So instead of that, obviously what we want is the really simple internal representation of a file, and we care about that, which, as you can tell from this slide, is trivial. So your open create or open at syscall returns a file descriptor, and that file descriptor is a number, and every process has its own set of file descriptors. Well, every process also has a task struct, which you can access from BPF. So when you're calling one of those syscalls and your BPF program runs, you can get the current task, and then you can do stuff with it. Well, that will have a link to the file struct, which will have a link to the file descriptor table struct, which has a link to the file descriptor array, in which you could look up that file descriptor, and that will give you a pointer to a struct file, which includes a struct path. And that struct path has a pointer to a dentry, which is a directory entry. And that directory entry has a name, and that name in this case would be password. Because it also has a link to its parent dentry, and its name would be etc. And then that would have a link to its parent dentry, which would be /. Obviously, every dentry also has, like, a mode and flags and who owns it and who created it, all those sort of stuff. Obviously, once you get to the /, well, that's the root on the file system that file is on. So then you might need to go, what's its parent? Well, its parent will either be pointed to itself or null, depending on implementation, which means you're at the root. So then you go to the VFS mount from that file, and go and have a look at where the file system has been mounted, which will give you a dentry for the mount point. And then you can do the same thing over that and recurse until you get to the root of that file system, which might be the root of the tree, but it might be the root of that particular file system mounted on another file system, and then you go and repeat. Obviously, this is annoying to do. A path name in Linux can have 4,096 characters in it. And if every one of those directories was a single letter, then that could be 2,048 directories, which is a lot of work to be doing when your complexity is limited by BPF verifier. But we can do this, and we can build technology that does this kind of stuff and hides it from you, so you don't have to worry about it. And we build in this notion of following a file descriptor. So there's a kernel function called fd-install, and that gets called every time a file descriptor gets allocated to a file. So on create, on open, etc., right? So if you catch or you hook on that fd-install kprobe, then you can see that it's got two arguments. The first one is the file descriptor, and the second one is the file that it's linking to. So we would follow the FD using the follow FD action, and that will then store a log of that. For that process, for that FD, it's pointing at this particular file, which we then know in a database by its actual name, its resolved path. So no directory traversals, no relativeness to it. It's an absolute path. And obviously, on closing a file descriptor, you want to take it out of the database because you don't want the database getting left dirty. So you can unfollow as well. So if you wanted to block writing to etc password, for example, then you might catch the syscall syswrite, right? If you wanted to do it at the syscall level, obviously you could do it further down. You might want to do it further down. You might want to do it after the buffer's been copied into the kernel memory, because that's the point when the buffer can be trusted. But say you just want to do it on the syscall because it's trivial, it's simple. Now you can see that the first argument is the file descriptor to that syscall. We can now treat that index 0 in our selectors as if it's a text string of the whole path name, and then you can match it. So if it's equal to etc password, block and kill access to trying to write to etc password. I won't demonstrate it for in order to get through the slides and leave some room for questions if you have them. But hopefully you can see that that's a much nicer interface to understanding files. Sockets, network sockets, also are a problem, and they're a problem for all sorts of different reasons. So mostly with syscalls, they're synchronous. If you open a file, you call the syscall to open the file, it switches to the kernel opens the file, and it switches back to user space. And that all happens in a synchronous, sequential fashion. And so when you're in the kernel, you're in the context of the process that opened the file. Hence, you can look up its task struct, get its PID, find out what binary it was, and match upon it, which is really useful. Network operations, not so synchronous. Because, of course, if you have a listening socket, when is that SYN packet coming into your socket in order to establish a connection? And then the kernel sends out a SYN-ACK. When it sends out that SYN-ACK, what context is the kernel running in? Probably not your process. Probably some other process, which is kind of annoying. Or when the final ACK arrives, from the SYN-ACK to establish that is definitely been connected to, your listening socket is now, established. Again, you're not in the context of the process. So you want to match the network action to processes. I mean, if you just want to build a firewall like IP tables, which doesn't really care about processes, then fine, you can do all of that without caring about these things. But if you want to know who's connecting to the outside world, who's receiving connections from the outside world, who's sending packets, receiving packets, etc., then you want to tie those to processes, because you want to build something that's smarter, more like a host IDS type thing. So how do you go about doing that? Well, we can track the sockets, which I mentioned earlier. This is socket tracking. And, I've got a point on the slide. That's annoying. So when the socket's created, which is usually through the skAlloc function in the kernel, then you could which is synchronous. Creating a socket is a synchronous action. You know which process created the socket. You can then just map from the socket identifier, which is usually the address of the struct sock, which just describes the socket, and map that to a process. Equally, you can untrack it when the socket gets closed. When you accept a socket, it doesn't go through skAlloc to allocate a new socket. It duplicates the socket instead. I don't know if you know that, but your listening socket continues to exist, and a new socket is allocated as the one that received the actual connection. I mean, your listening socket might then immediately close if you're only listening for one connection, perhaps, but it's a different socket. So you need to track that as well. But tracking it really is trivial, as you can imagine. So there's a bit of YAML for socket tracking. So we're hooking on skAlloc and sk3, sk3 being like closing a socket. And all we're saying is we're going to match the family to family 2, which is IPv4 in this case, because we care about IPv4 for this, but you could care about other families if you want, or just not bother matching on it. And then the action is, it's on the return arg action is track sock. So the return of skAlloc is the struct sock pointer. So we're going to take that on the return, and we're going to map that to whichever process did it. So if you wanted to track TCP connects, then you could track them by whenever Tetragon then sees a struct sock in an argument, it just looks it up in its database. And if in the database it exists, it then rewrites the event that it's going to send with the process of who owns the socket, not the process that the kernel is currently in the context of. So it solves that problem. The bits in green are just showing some of the matching type stuff you could do. So it understands a sock structure. So you can match on the destination address, for example. So in this case, anything that's going to localhost, it would match upon, and the same for the close. So you could match on, CIDR addresses. You can match on ports, states, etc. Catch all the listens. You could do this. So CSK listen start is where what gets called when a socket goes into listen mode. Again, when a socket is accepted, we can see the state change. So the state changes of the socket from listening to established. We could catch that by with a bit of YAML, and we can track the sock that was created, the duplicate sock, by adding the track sock as well. But what about UDP? Because TCP is really obvious. It's all connection based. We only have to catch the connects and the closes and the accepts and the listens and things like that. But with UDP, there are none of those things, obviously, being connectionless. You kind of have to observe every datagram. I don't know if you're aware, but when you create a UDP socket, it's not like a TCP socket in that it has a set, a set source and a set destination. With the UDP socket, like the source could be set to a local port or whatever, but the destination, you can send anything you like. You can send to. You can receive from anywhere, receive from. And so you can have a whole load of packets or datagrams arriving at your socket or being sent from your socket that don't match the underlying sock. So in which case we need to look at the SKB, which is the socket buffer, which is in kernel speak a datagram. But obviously every datagram would be expensive. That's a lot of information to be sending from kernel to user space. You probably don't want all of that. So we use a similar thing to what we did with Sysmon. So Sysmon will tell you every new UDP packet, every new tuple that it sees within a 30-minute window. So, and it will consider those to be a new connection. I mean, you can imagine, like, your process jabbers over, like, UDP to somewhere. It's UDP port 53 or something. You only care about the first packet to it in order to know that it's talking to that particular service. So every packet that comes after that, it's going to ignore until the timer runs out, and then it will report it again. So if you had like a DNS tunnel, every N time you'd see another one of those messages to say it's still talking on this port, but so it minimizes the amount of data that you have to throw around. And again, UDP is really trivial. You can just like hook a point which sees every datagram. You can match it on, where it's going. We can label, so in green, another thing you can do is you can label your argument. So the argument there, the second, argument 2 is, the enumeration of C group BPF attached type, which is basically how is this thing attached. And, it could be 0 or 1 mostly, like, ingress and egress. So if it's a 1, it's going to be sent. So we could label, so rather than just having in your JSON, or sort of output in your logs, that argument 2 was a 1. If we label it send, it will say argument 2 was a 1, and it's called send. So it gives you a bit more information which your SIEM could then make use of. But using something like this, you can then catch all of those things and therefore get UDP sockets. So where are we going? I'm going to add IPv6 support. If you've ever done any IPv6 coding from a parsing perspective, parsing datagrams and packets, you'll know it's really hard. Like IPv4, trivial in comparison, but IPv6 has any number of extension headers, and each extension header needs to be parsed in order to get to the next extension header. And you have to parse through all of those before you get to the actual transport, like the TCP or the UDP part. So obviously it's a bit more tricky. But I've already implemented all that on the enterprise version, so it's a case of just copying and pasting some code down into the open source one. So IPv6 support will come. We'll improve the file ops. Like, they're okay, but again, in enterprise, we've got a lot further, and a lot of that will be open sourced and brought into the open source version. Usually, I say we actively develop the open source version, but we also actively develop the enterprise version against customer requirements. And so if someone's paying, then obviously we're going to add that into the bit that they paid for. And then the process is, how can we get that open source? How can we provide that to everybody else? So that's why it's in that kind of order. We're going to try and make the configurations more user-friendly. So instead of having to write all of that YAML, if you just want TCP connects, why can't you just write a small amount of YAML that says, I want TCP connects? And then behind that would be all of this other YAML. You can still write all of that YAML, and you can still tweak it and attach it to a different point and all those sort of things, and still access all of that YAML if you wanted to write your own. But at the same time, if you just wanted to do the easy bit or the obvious bit, then why can't we just have a simple configuration language for that, which is where we're going. And also on the output. So you saw the JSON output. It's quite readable. You can put that into a seam. You've got all these fields. It's hierarchical. You can understand it. But why can't that just be, there's been a connect, there's been an accept, rather than a kprobe occurred on this particular function and it did this. So that's where that's going. And obviously there'll be more examples, more documentation, and hopefully where we're heading is a repository of useful policies, so you can build up your logging system based on examples that we know work for different cases. And this year we will get to version 1.0, which means that the code will become stable, rather than in beta, essentially. And there'll be a big fanfare for that, obviously. But a lot of these things that I'm talking about will become better when we get to that point. So, in summary, you're doing logging wrong. Unfortunately, you can detect what your logging system will let you detect. You can't detect anything else. What Tetragon will let you do is hook where, or BPF itself, if you want to get down to nitty gritty and code it yourself. But with BPF, you can do this in YAML. You can hook what you want to see at the place where you want to see it, and decide upon what you're seeing, what you want to do about it. And what you might want to do about it is detect it, alert on it, lock it, kill it. We've built in useful stuff for file and network, which you won't find elsewhere, which is kind of useful. We're going to build upon those things and create more useful things that you can get access to from the YAML. And we know this is the start of a journey and we've got a long way to go, but we are actively committed to continuing this journey and getting to a place which is going to be awesome, because we really do think that this is the solution to logging. So with that, and with apparently 7 minutes to go, and I know it's lunchtime coming up, does anyone have any questions? Yeah. So the question was, why is it different to, say, file search or audit beat, file beat, etc.? It's because those systems, it's kind of what I was saying before, you're constrained with those systems to what they'll let you log. Most of those things are syscall based, so you only get it at the syscall level. Some of those will be vulnerable to the phantom attacks that I talked about that you can get from the DEF CON 29 talk. What's different here is that you can get under the covers and go to whatever it is that you care about, and log that particular thing. So future things that are going to probably come at some point is things like mmap protections or mprotect. So, you know, when you change the page to make it executable from just being writable, that's the sort of thing you might want to log. But you could log it at very fine-grained detail. And at the point where you detect somebody making a writable page executable, which is usually in the first stage of like a ROP attack or something, you can kill the process dead from the kernel instantly. You know, with a lot of those other systems, You've got to pick up the event from your scene and then do something about it, which might well be too late. So, yeah, that's the sort of thing that makes it different. Yeah. Yeah. So the question was like, can it detect the changes in config? And yes, the answer is yeah. It'd be more a case of this, yeah, well, it'd be more a case of the buffer before was this, or the buffer that's being written is this, and then you'd need some user space code. In Tetragon Enterprise, then that is easily something we would build if a customer requested it. It's trivial to do. But again, it's just explaining some of the power that you get from this sort of thing. One at the back.
Website, we're going to labs on this stuff, they're hands-on labs, and they're really well done. So go out there and think.
Yeah, thank you. I should have mentioned that. Our development website has a lot of labs, which are free, and you can go ahead and do them. And you get badges, I think, now for completing them, which is always great. Look, people love badges. If there's nothing else, shall we all go and get some food? Yeah? Thank you very much.